Good, looks like a small round today. Either way, you can let me know how you get on with the exercise sheets. And we'll continue with some fixed parameter tractable algorithms. Maybe I'll give it a minute or two. Morning. Hey guys. Good, let's start. Welcome guys. And ladies and gentlemen, I guess. I guess the second question is a reasonable state to be in. If you didn't look at it now, it might be not enough time to solve some of the problems. Writing up hopefully is more plannable. But of course, there's exercises, and the first one is due tomorrow. You can submit in the same groups you used for the mini seminar, but you could also, I guess, in principle, groups can also change. That's all right, but it's the same group sizes.
When should we get the points for the mini seminar?
When?
Should we get the points, like the scores we get for the mini seminar? Notes, the marks.
Sure. You'll get some once it's marked. I guess Mohammed is on it. But we were waiting for the peer reviews as well. They're part of the assessment. And though these were only collected on Sunday, or a few people sent them in Sunday. So we're looking at those this week. And then you should hear about the mini seminars well soon. There's a bunch of videos to watch, so as you may have seen, it takes a bit of time. And the exercises kind of just fit in the same slot. You earn marks as a group, and you need to pass 50% in total. That's not the right thing. That's better. If your question was where you get the marks, that's on Elias. Like where you submitted it, you should get some a short written feedback and some points as well. We left off last time somewhere in the middle of the section on kernels, and we showed this nice result about FPT algorithms and kernelization. Maybe just a brief recap. Kernelization was the idea of pre-processing the input so that it becomes smaller. And of course, pre-processing in general can be anything. Kernelization specifically needed to be so that the new instance we create is bounded in size by a function just of the parameter of the original instance. Then we call a pre-processing rule a kernelization. And of course, the point is, after you've reduced the input, now you can run any algorithm, even if the input size, in terms of the input size, it takes exponential time. It will still be overall an FPT algorithm because you've shrunk the instance you run this expensive algorithm on. to a size that's only bounded in terms of the parameter. And we've seen some examples. We'll see one more. But in particular, maybe not so obvious. So what I just said is if you have a kernelization, you can use that to build an FPT algorithm by running the kernelization and then solving the remaining problem with almost any algorithm. But the converse is also true. If there's an arbitrary FPT algorithm, you can always turn that into a kernelization, even though it's not a very informative one because it's not super explicit. It depends on running some algorithm for a certain number of time steps. And so this is not normally how you would construct kernelizations. So in a way, kernelizations are still somewhat stronger. An FPT algorithm gives you a hypothetical kernelization in the way we showed, but it's not as explicit, whereas the other way around is a bit nicer. So people often try to express things as a kernelization if possible, and then also bound the size of the result. And in this case, there's one last bit in that section left where we'll look at the maxsat problem again. So specifically P maxsat, which means it's parameterized by the second, the threshold that you give it. So K is the number of clauses that you would like to satisfy. And what we'll show is that you can, for this problem P maxsat, you can construct a kernelization. And also the resulting kernel of the problem is bounded by a reasonable function of K, not just some arbitrary, potentially a very fast growing function, but just K squared. So let's pick some example just to make it a bit explicit of some formula. So this is, remember maxsat, it doesn't need to have a strict form for the literals, for the clauses, but it has to be in conjunctive normal form. So maybe it looks like this. And there can be stupid and redundant clauses in general. I'm just using this short notation with a bar on top to denote the negated literals. So we'll often think of a formula like this to be given as a set of sets, namely replace the outer and by one set, and then each clause is also a set of the literals that are contained in it. The reason for that is just we don't actually care about the order of the literals in a clause, and also the ordering of the clauses is not really important, although we sometimes need to give them names. But so you represent a formula like this as a set of sets. The outermost is the set of all clauses. The innermost sets are the set of literals, one clause each. Okay, to make as a first simple step, you can say it's an assumption, or you can enforce it. Say each variable only occurs once per clause. This is kind of implicit with the set notation. If you talk about literals, and if a clause ever contains a variable and its negation, you just cross the two off because they're the literal will always be satisfied. Right? Then you can remove that literal. So standard notation we had before, I think, is the number of clauses is m, sorry. I'm using m because n is reserved for the input size, right? So n is the total input size. And we'll have to encode this in binary at the end in some form. But really, the main thing, you could think of it as the total number of literals in all clauses. And maybe there's a log factor missing for specifying which variable you mean in each case. Okay, now let's do something about the actual proof. The first observation is if k is small, the whole problem is trivial and we can get rid of that case. If k is specifically less than half, at most m half rounded down, then I can always satisfy at least half of the clauses because you pick an arbitrary assignment for all the variables. Does that need a name? Maybe not. Let's call it A. And now what's going to happen? A is going to satisfy a certain number of clauses, right? And we don't know what L is. But clearly, if L is at least K, then we're done. We can just output a yes. It's a yes instance. We found a satisfying assignment for that instance. The other option, if L is less than K, then it's specifically less than m half. Then you're doing the opposite of whatever A does, because if A does not satisfy these other clauses, it means every single literal in these clauses must be false, right? So if you just invert the variable assignment, those clauses turn true. It satisfies m minus L of the clauses. And then if L was smaller than half of them, this has to be greater than half. And so greater than K. And so we could, again, turn it into a yes instance. So indeed, whenever that's the case, we can output yes without doing anything. So if you want to be strict about the kernelization, you just output a trivially satisfiable, a satisfiable formula of constant size. So for the rest, we can assume that K is not tiny. So as a second case is K is at least m half rounded up. And so can we use that somehow? Well, you can just turn it around to bound m. The number of clauses then can't be too large in terms of K, right? Then m is strictly less than 2 times K, just because of the rounding. Sorry, I guess the case should be phrased like this, because that's the negation of that. And that also works in the even case. If m is even, then this is exactly m half, and here we have strictly greater than m half. If m is odd, then this was rounding down, but then this is rounding up, and then again, k is strictly greater than m half. So maybe if you want to make this more explicit. Okay. So we already have the number of clauses is not too big. That's not a kernel yet because each of the clauses could be really big. And the kernelization needs the overall size of the formula to be small. And so we now split the formula up. Into those clauses that are already small enough. And we're aiming for a kernel size of k squared. So if we have roughly k clauses, k literals per clause is okay. That gives us a k squared size. But the clauses with more than k literals, we have to take care of. And so we have the large literals, FL. There'll also be the small literals. These are all the clauses C in the formula so that C has k or more literals. And conversely, this is all the others. And now, again, an observation. If we have a lot of these large clauses, then that's an easy case. Say we say capital L is the number of long clauses or large clauses. Now, if this is greater than k, then we have these really long clauses and k of them. So it's enough if we satisfy only these k clauses, only long clauses. Now, because they each have at least k literals, they also have to talk about more than k variables, at least k variables. That was our assumption up here, right? The variables occur only once in each of these. So we have k clauses, right? K large clauses, each with k variables in them. So we can pick a disjoint collection. We can pick one variable per clause and assign it so that that clause becomes true without making any of the other clauses false. Because there's, we can pick this one here, this variable here, this one here, and they're disjoint. I guess unique is a bit important. Yeah. So if we're in this case, many long clauses, we immediately output a yes instance. And we're again done. So if we detect this case, again, output a trivial yes instance and you're done. So what's left is the case L is less than K. What can we do in this case? In this case, we have to work a bit harder, but we can use the following. We consider now the instance where we just look at the short formulas with the parameter reduced so that we only have to satisfy, so we're kind of satisfying all the long clauses by the same argument. And we try to satisfy from the short clauses enough clauses to in total get to k. Okay. If that is a yes instance, then the original also is a yes instance. And the reason for that is, so this is it's an if and only if statement. So we're proving the two directions separately. If there's a satisfying assignment for k minus L clauses in Fs among the short clauses, now we're trying to extend this so that at least that all the long clauses are satisfied. Now, each of these short clauses has to be satisfied because of some literal. Otherwise, it wouldn't be satisfied. Now, the point is we don't have to satisfy more than one literal. So we could pick one true literal from each of these short clauses. And so that fixes at most k minus L different variables, because there's only k minus L clauses. So we pick k minus L literals that have to be true. K minus L are important. So what I mean by fixing here is I can take the assignment and I can flip the value of the remaining variables without making these k minus L short clauses false. And so that means I have a lot of variables left that I haven't used. In particular for the L long clauses. They're each at least k variables long. K minus L might already be taken, but I'm left with L variables that I can still assign, and I have to be able to find a disjoint set for the same reason as before. The clauses are long enough, they must contain many different variables, there must be a selection of L different ones. Okay, that proves one direction. If we look at the other direction, it's actually easy. If we can satisfy k clauses in the all of F, then I I only have L big clauses, so even if I satisfy all of them, I must leave k minus L clauses to be satisfied among the small ones. So I'll save myself the ink there. So now that we've established this, again, this case was easy. In this case, we've reduced the problem to something smaller. Now we only have small clauses, right? So let me just write this down again. Only the short clauses with a slightly different parameter. What's the size of this problem? Well, it has at most m minus L, so at most m clauses. But remember what we learned about that. If we're not in the boring case, then this is at most 2 times k. And each has at most, well, strictly less than k variables indeed, literals. Because we're only looking at the short ones. So if you multiply this up, the total number of literals or the overall size, number of literals is order k squared. And if you want the encoding size, then maybe there's a log factor needed to specify the variables, but maybe this would be the more true answer. But we're often not fuzzy about the encoding in binary specifically. So we'll be happy with a natural parameter like the number of literals in the entire formula. And that's the end of the proof. We've output a kernel in each of the cases. You can trace the steps again. There's only one where the kernel is non-trivial. In all the other cases, it was just a constant size yes instance that you can arbitrarily pick. And because of our previous theorem, the last one we proved before, we have a kernelization for P max sat. That also means P max sat is in FPT. There's the complexity class of all problems that have an FPT algorithm. Okay. That's the end of the kernelization part. If there are questions about that, maybe it's good to discuss them first. Also, just my reminder for everyone, because some of you arrived late. There's an exercise sheet due tomorrow, and people moved their votes from the last one to not shock me too much. Submit it on Ilias. You'll get feedback on Ilias. Then at some point, well, there's the person to say well how long it'll take, but a couple of days. And I'll also tell you. I think the vote is still, or the poll is still open for the tutorial session. It seems a majority prefer, or a slight majority prefers the slot right after lectures, so after lunch on Tuesdays. So it gives us very little break, or we could move it slightly later. I'll see how the availability for rooms is as well. Okay, if there are no questions on the kernelizations, then I have some more examples on nice algorithms. And maybe so far so some of the algorithms are a bit underwhelming so far in that they satisfy the definitions of FPT algorithms, but they're not super exciting in that they don't exploit much of the problem-specific properties to do anything non-trivial. We've just taken simple algorithms mostly and given them a new name. We called them FPT algorithms because they happen to have a running time that's only exponential in some parameter. But the real fun only starts when you look into the problem-specific properties. Also, one remark I wanted to make at this point, because we've proven this nice theorem about P max SAT, but if you scan through the proof, it also really means that the number of clauses to satisfy is not such an exciting parameter here, because it cannot possibly be small. That was the very first simple argument here. If the parameter is small enough, then it's a trivial problem. You can always satisfy half of the clauses. So a parameter is a good parameter if it can be expected to be small in practical instances of the problem. But here, by and large, it has to be linear in the problem size. So it's great that we could find this small kernel, but it's only small in terms of a parameter that won't normally be small, right? In the next section, we return to the depth-bounded exhaustive search technique that we've seen before for a few introductory examples. And I have a few more examples that take some more properties of the input into account to do something that's maybe not completely obvious at first that it's doable, but they fit in this schema of exhaustive search as well. That's what I just said. There were the previous examples were basically simple brute force algorithms, and we'll try to look a bit closer now. This one I've moved, so you can't recall this. We will see. We'll see that the problem of independent set in a graph. So remember what that is. You're given some graph, undirected graph, could have cycles and whatever, could look complicated, doesn't need to be connected in general. The task in the independent set problem is to find a largest set of vertices that are mutually unconnected, so no edges between any of them. So what's a maximal independent set here? I suppose I have to pick these. I'm guessing it's a good idea to pick these leaves, but it's really a hard problem, so I might not get the optimal solution this way. Probably these two, and that's all. Oops. So I guess that's a maximal independent set in this case. Or maximum, I should say. That was the independent set problem. Now I haven't told you what W1 hard means. So just forget about it for the moment. We'll come to that probably tomorrow. We'll start with that part tomorrow. What this means intuitively is we shouldn't expect an FPT algorithm for this problem in general. Okay. As often in complexity theory, we can't really prove that. Same as for NP hard problems, we can't prove there's no polytime algorithm, but it's a bit unlikely. So what we'll look at here is a restriction of this problem where the graph that we're given is planar. And indeed, the example I've chosen is a planar graph, just because they're nicer to draw. So first of all, I'll define this a little bit because I don't know how much graph theory background people have. So it's the same problem, just that now the graph is planar. And the rest is the formalization of what I've shown on the example. We're given a parameter and we try to find k vertices that are mutually not connected. I've shown you the optimization version of the problem. Now, what's a planar graph? Maybe would be a useful question for Slido. Who knows what planar graphs are? Who doesn't know what planar graphs are? Have you heard the term before? So a planar graph is a graph that can be drawn in the plane like this without any edges crossing. So embedding is the formal term, but you can think of it as a placement of the vertices in just the Euclidean plane R2. And I'm just going to say a drawing of the edges. You can make this more formal, but maybe it's not needed here. No, stay. Now, if you come up with examples, maybe it seems like every graph should be possible to be drawn like this. A famous example that is not planar is the K33, the complete bipartite graph with 3 vertices on each side. So every vertex here connects to every vertex on the other end. But it's bipartite, which means all the edges go from one set of vertices to the other set of vertices. Here we have the lower and the upper vertices, and there's no edges that stay among the lower or among the upper vertices. And now the way I've drawn this graph clearly has edge crossings. Now the trick with planar graphs is all that counts is the graph with the set of vertices and edges. My drawing is just one drawing. Maybe there's a better drawing. If I'm smarter with routing the edges, maybe there is a way to not have them cross. But here the answer is no, there is no way, and provably so. And I guess we'll see in a second why. I mean, it's a classic and simple argument. Another example is K5, the complete graph of 5 vertices. A bit more messy to draw. Initially looks like a nice thing, but now, is that all? Yeah, it looks like everything has 4 edges. So that's the complete graph on 5 vertices. That's also not planar. And then there's a cool theorem that essentially these 2 graphs are the only obstacles. Whenever a graph is not planar, it contains a potentially concealed instance of one of these 2 graphs. That's a deep theorem in graph theory that we won't need for now. So you can forget about this. So that's a nice way to check if a graph is planar. So we're looking at this independent set problem, and maybe you can get an intuition that potentially this problem is easier on graphs that are not like this, right? These are forbidden now. Only graphs like this where I can draw them in the plane. Maybe you have get a feeling that the problem might be easier on these graphs, just because things are separated out. If they're far away in the plane, then maybe there's also no edge between them, because it would probably cross a lot of things. But this is very vague. That's not the way to prove anything. What we'll show at the end of this part is that indeed you can do independent set on planar graphs with this running time, which is a fixed parameter tractable algorithm. And remember, for the general problem, this is unlikely to exist. So the restriction to planar graphs here really helps us. And whether 6 to the k is a good running time is a different question. I'll only show you a very simple algorithm, which indeed, this is the worst case. It's often much better. But how does this work? How can you exploit this property that the graph can somehow be drawn in the plane, which is not even clear how to construct this if you first see planar graphs. So how can we use this to do a faster search for independent sets? Okay. We'll use a bit of background knowledge on planar graphs, but it's all fairly fundamental. Now, I'm saying this from today's perspective. It all builds on famous results, including stuff from Leonhard Euler and so on, which at the time of their invention was, I guess, fairly non-obvious. But I can explain all the concepts on one slide or two. The famous result that Euler proved is summarized with this equation. Whenever you have a planar graph with the additional restriction that it's connected, again, algorithmically, that's not a problem. If I have an instance of my independent set problem with several disconnected parts of the graph, I'm just solving the problem independently on all the disconnected parts. And the independent set of the entire graph is the union of the independent sets of the parts. Right? That's what happened here as well. In my drawing here, the graph was disconnected. There was an isolated vertex, there was this tiny component, and there was this bigger component. And I could just independently solve the problem on each of them. So assume for this part that the graph is connected. Then it has n vertices, m edges, and f faces. That's not defined. There's the faces missing, which is in such a drawing is the regions of the plane that are cut off by edges. It's a very graphical kind of notion. Then you can relate these numbers, and in any connected planar graph, this equality holds exactly. It's a powerful tool. I'm not going to prove this, but I'm giving you some idea for the proof, because you can almost prove this inductively. So first of all, let's make clear that the terminology is clear. So I'm drawing a tiny planar graph. And there can be funny business like this as well. So let's quickly count the three quantities here. What's the number of vertices? Well, 1, 2, 3, 4, 5, 6, 7. Okay, you correct me if I'm doing stunt nonsense. 7. Then the number of edges. 1, 2, 3, 4, 5, 6, 7, 8. And the number of faces, now this is, maybe we can shade those a bit. There's one face. There's another face which goes around this vertex. This is still the same face, right? And then there's the outer face, which is everything outside of the graph. So we should have 3 faces. And now if we check the formula here, we have 7 minus 8 plus 3, which indeed is 2, right? 10 minus 8. So it works out in the example. That's good. That's not a proof, though. I'm not claiming a formal proof, but I want to give you an intuition because I think it's just so nice. And there's enough people that haven't seen, not to have seen it. So effectively, it's an induction on the number of faces. If you look at graphs with a single face, how can these possibly look? No graph can get rid of this outer face, the dark blue one. So the only option to not add another face is to avoid any cycles. As long as I'm never closing off a part, I keep one face, and whenever I close a cycle, I must enclose another face. So if I have a single face, then G is a tree. And then basically it looks something like this. It might branch off. It can have arbitrary degree, right? It can have long branches, or it can have high degree vertices. But it will always look something like this. And computer science basic knowledge question?
You said no graph can avoid getting the outer face, but
Sure.
the one you draw, for example, has 0 faces.
Which one?
The one you draw.
This one?
Yeah.
It still has one face, namely the outer
It
face.
doesn't close anything.
Right. But there's still one, so a face is a part of the Euclidean plane, and if it's enclosed by edges, then it's also a face, but also the thing that is on the outside of the graph is one face. An alternative equivalent way to view it is to see the graph embedded on a sphere. Then there's no outer and inner, there's just faces. It's very annoying to draw spheres and make it clear and visually, but if you have good 3D imagination, maybe you find it easier to imagine this wrapped on a sphere. And then this blue thing is just the thing that wraps around the back of the sphere. And it's not a special face in any sense. It's one of the faces that it has. And if you take a sphere and draw a tree on it, there's still the sphere. So, but it's a good point. I guess it's how to define faces properly is maybe tricky. So faces should be thought of as regions of the plane. Now, computer science basic knowledge is in a tree, there's one more vertices than edges. And the simple picture proof would be pick any vertex, say this one, and orient all the edges towards that guy. If they're far away, there's still a unique path because there can't be cycles. And once you've done that, every vertex has exactly out degree 1, apart from the poor guy we chose, which has no out degree, right? So here, always n is m plus 1. And if you plug that in, it satisfies the equation. Okay? So that was the induction basis of this induction. And then the inductive step is take any graph and a drawing and add another face. How can that happen? And it basically happens by closing another cycle. That's virtually the only way how you can add a new face. You have to somehow close a cycle. And that's the part where I'm just giving you some idea, and I'm not trying to do a rigorous proof. How could things look? So there could be many weird things how a face could be created. Maybe this is our graph that we start with. Currently has 3 faces, right? The outermost and these 2. Now, one way to create another face would be to close an edge here. That would add this face, and it would add 1 edge. Another option would be to draw an edge in here, which cuts one of those cycles in half, adds another face. Another option is to connect this one, but in each case, what I'm doing is add 1 edge and close off 1 cycle. So I'm getting a plus on the edges and a plus on the faces. That's the key operation. And if you look what happens here, the difference between faces and edges doesn't matter. I can add edges. If I also increase the faces by the same amount, I won't invalidate this equation. And you can think about what else can you do to a graph to grow it? Well, you can add vertices. If they're isolated or just connected somewhere, then they don't add a face. So if I'm adding a vertex here, something like this, I'm making n1 bigger, but also m1 bigger. And I don't get another face. Then again, the equation is satisfied. It's kind of, I'll stop at this point. The idea is that this formula can be proven by going through all possible cases, how you can modify a graph. And you can use induction on, say, the number of faces to see what happens in each case. Okay. So far, so good? I guess it's yeah, we normally don't allow loops where when I say graph, I think of a simple graph. Does it violate the formula though?
Example, 2 vertices, 1 and self loop. Yeah. 1 edge and 1 self loop.
Like this?
Yeah.
So you have 2 faces, 2 edges, and 2 vertices. That seems fine, right?
Right. Okay.
It seems right. So it has to be connected. That's definitely like the way to break it is to just say I have 2 vertices, or I have 4 vertices and they're not connected. Then things break. That's why the connected here is important. It's an interesting point what happens with self loops. For most of the algorithms, I think I'm implicitly assuming simple graphs, but I think this specific theorem would actually work fine. The same argument here seems to work. Right. Let me just do this in dotted. I'm also adding one edge and 1 face, so I don't think it breaks. Okay. What we use this equation for is the following simple observation, which again is something to keep in mind about planar graphs because it's useful in many places. And here we need simple. If I have a planar graph, a simple planar graph with no vertices and edges, I can bound the number of edges it can have simply by using that formula and the fact that faces can't be arbitrarily small. So what's the smallest face I can make? Well, I could try to do this, but that's not allowed in a simple graph. Then I would have a face that's delimited by just 1 edge. I could try to make a face that's delimited by 2 edges, but then actually these would have, again, they connect the same vertices. So this is also not a simple graph. So the smallest configuration I can make that closes off a face is a triangle. Okay? So in a simple graph means every face is delimited by at least 3 edges. And so whatever my graph looks like, I can just count how things go. So let me again do this mostly by example. Might actually be enough. So I have 3 faces, this one, and the outer face. I must have 3 edges, three edges for each of these, but I'm double counting each edge exactly twice. right? Okay, I guess that's not true as I wrote it here. Summing over the edges that delimit a face would double count every edge twice. If I say I use the minimal number as it's at most. So I get a bound on the number of edges. But then I can also insert what I know about f. Let me move this a bit. So what do we get? 3 times, and then it's 2 minus n plus m. I'm just solving this for f, and hopefully don't goof by doing it. And so stay here. That's the overall thing. Now you can simplify this further. So it's 6 minus 3n plus 3m. So you now have the entire equation, and I'm subtracting 2m from this. So I take this equation, minus 2m, and bring this part to the other side. So also plus 3n minus 6. So I'm left with m on this side. And on the other side here, I get less or equal 3n minus 6. Is that clear? I'm just taking this one equation, right? 3m greater equal 6 minus 3n plus 3m. And moving things on the other side, I get exactly what we claimed. So this is cool because it means the number of edges in any planar graph is at most linear in the number of vertices. All planar graphs are sparse. It also means that the average degree of a vertex cannot be very big. Just because the summing up all the degrees for this second part, summing over all vertices and then the degree of a vertex, that counts every edge twice, once from each endpoint. And so we know this is at most 6n. And so you can divide by n, and then you get the average. Average degree is at most 6. And because there's actually 6n minus 12, you get a strictly less here. That's where the strictly less comes from. Good. Fine. This also means, maybe it's worth listing explicitly, what follows from this, that the average degree is less than 6. This also means I will always have a vertex of degree at most 5 in any planar graph. And the proof is by contradiction. If all vertices had degree at least 6, then the average would be at least 6. It's as simple as that. You could call it the probabilistic method if you want. the expected value, if you draw a random vertex, the expected value is less than 6, then there must be a vertex that's below the expectation. Of all this prelude, this is actually the statement that we're going to use. Okay? In every planar graph, there's always a degree of a vertex of degree at most 5. And this property is also called the degeneracy of a graph. So degeneracy means is the property that in a graph I can find a vertex of at most that degree, and also if I take any induced subgraph, the same is true. Say degeneracy D. And while we're doing the detour on graph theory, do people know what an induced subgraph is? There's often this notation, if we have a graph GVE, the standard notation I know is this for induced subgraphs. So where V prime is some subset of the vertices. It's a simple thing. It's just the graph where you take the subset of the vertices and you take all the edges of the original graph that only talk about vertices in V prime. A concise way to write this is to take the edges as a set of 2-element sets, or yeah, I guess I'm cheating a tiny bit here. Maybe I should write it out just to be formal. It's all the edges in the graph UV. So that U and V are in V prime. And the same edge exists in the original edge set of the graph. That's an induced subgraph. You only focus on a subset of vertices, and you forget of all the edges that would have a dangling end. That's all. But this notation is useful because I think I used it in some pseudocode. So keep that in mind. If you have a graph and then square brackets with a vertex set, that means induced subgraph. And so, yeah, this is. That's that notation. Brilliant. Maybe you also have a feeling now how this independent set algorithm could work. Let me just go back to the claim that we had a while ago. The claim was, if I have a planar graph, I can find independent sets with that running time, 6 to the k times n. Now, this constant 6 popped up here as a bound on the degree or the degeneracy. So maybe this is not so far away. And indeed, the idea is for independent set, if you have any vertex, one of these days again. If you have any vertex and its neighbors, you can only include either the neighbors or one of the neighbors or the center vertex in an independent set. You cannot include both because that vertex in the middle is connected to the others, so they are not part of an independent set. Oops. Okay. this cable. So let me just draw the picture for what I just said. If I have this vertex and its neighbors, if I'm the point is independent sets can be any subset, but if it's an independent set that has any chance to be maximum, so a maximal subset means can't add more vertices to this set. Without making it non-independent. If you have a maximal independent set, you have to take one of those 5 vertices. If you did not include any, then you could have taken the center and added to it. Because you're not including any of the neighbors of this vertex V. None of V's neighbors in the set could add V itself. So any maximal independent set, any of those that have any chance of being the largest, they must pick either the center vertex or some of the neighbors. They could include many of the neighbors, but at least one of them. That's the idea behind this algorithm. And so what it does is obviously a depth-bounded search. That's still the chapter we're in. So we're given a graph and the parameter, which is the size of the independent set we're trying to construct. If k is larger than the number of vertices in the entire graph, then we're certainly out of luck. Whereas if the edge set is empty, then that's easy. We can just return the entire set. Everything's independent. And otherwise, if we're not in the boring corner cases or base cases, then we have to choose a vertex as the basis for this star. And here we can pick a vertex of minimal degree to reduce the number of choices. So we have a vertex V and its neighbors. And because the graph is planar, we know that this minimal degree vertex will always have degree at most 5. That's just by the magic of planarity. And then we go for each of these vertices, we try including that vertex in the independent set and recurse. One of them has to succeed. Or, well, I should say, if anything succeeds, then a solution with one of them has to succeed. So formally, this looks like I'm constructing a partial solution. I'm constructing the graph where I've removed the vertices that I'm dealing with now. So I remove this vertex and its neighborhood, because if I pick one vertex, I cannot include any of its neighbors in any independent set. So I take the vertex U and all its neighbors. That's what that's supposed to mean. I remove those from the vertex set, and I remove all the edges that have an element in there. So I could have written here GU is G reduce is the induced subgraph on V without D. And then I try recursively to solve the problem where I only look at this graph and I have one less vertex to include. If that solution is indeed successful, I should add vertex U, the center that I picked. So we try this for all the options, either this vertex V in the center or any of its neighbors. And if any of these solutions succeeds, that's great. Then we return the largest of those, might as well. And if none of them succeeds, then we know there's no possible solution. We've tried all maximal independent sets, and so the maximum independent set can't have size k. So maybe on this slide it's convenient to analyze the search space. We still have to show this running time. So because of planarity, we know D is at most 5, but I have to include V. So we have at most 6 recursive calls in each call. And we may have to go all the way down. Sometimes we're lucky and we can abort early, but in the worst case, we have to go down until k is at 0. That's the is there a base case for k equals 0? How do we stop if k gets smaller and smaller? And eventually the I guess it has to be that the graph gets too small and then we can't continue. So in the worst case, how do we bound the depth? I guess there's a case missing. If k is 0, we should just return the empty set and stop. I don't see if that's somehow implicitly caught in any of the other cases. This is the worst case, that we don't stop before that happens. So we go down with k all the way. And so we branch out 6-fold in each step and we go k steps down. That gives us a search space of 6 to the k. Again, this is just the worst case. Most graphs won't have the maximal degree equal to 6 all the time. It's actually it's hardly possible in planar graphs, but as a simple bound, that's the best we can say. And then how costly is each recursive call? That depends on how you implement things in detail, but you can say it's linear in the graph size. And so because here n and m are linearly related, each takes linear in n and m, and that here is just linear in n. So the total size, the total running time is bounded by the 6 to the k and then times n as we had it in the claim. Okay. So one remark is that indeed the 6 to the k may not be the absolute best possible, but some exponential dependence on k is likely not avoidable, because the problem is still NP-hard even on planar graphs, when the vertex degree even is at most 3. So even a much more restricted version of independent set is an NP-hard problem. So you can't expect to solve it in polynomial time, but this FPT time is possible. And the same algorithm works for any bounded degeneracy graph. All we needed, or all we used, was there's always a degree D vertex, a small degree vertex, and then we can bound the running time in a similar way. Okay, this section I should have broken into parts, but um, it continues on for a bit. Not a ton of time left. Maybe we'll crack on and stop a bit early. Or does it make sense to have 5 minutes break and then continue for 10 minutes? I don't know. Break? Okay, good. Let's do slightly shorter break so you're not late for lunch. Okay, 36 on my watch. The second example is far less involved, so maybe we can actually do it in 10 minutes. I think in hindsight, I should have put this first. The planar graph thing is kind of trivial if you know planar graphs well already, but I guess is less trivial if you've seen it the first time. Whereas this one is a very elementary argument. But I thought it's nice to have a different flavor of problem. We've talked about graphs a lot. So in this case, we're talking about strings, and it's also a problem of lots of practical appeal for bioinformatics applications. So it's the closest string problem. think of it as a consensus string. You're given some strings, a collection of m strings, all of the same length. The problem we've actually defined earlier as one of those NP-hard problems, but I'm just repeating it here. And we're given a threshold k. And the question is, can I find some string, not necessarily from the collection, but any consensus that might lie in between the given strings, so that the Hamming distance between these strings is not too big. It's at most k. Again, Hamming distance is just you count the number of mismatch positions. So green means there's the same character, and then maybe there's at other positions the strings differ. And you just count the number of places where they differ. So here the Hamming distance would be 4. It's the simplest kind of metric on strings you could imagine. You just count how many characters are not the same. And even for that, the problem is already a bit tricky. So this consensus string, you can think of these as kind of genetic sequences, and you're trying to find a common ancestor in evolutionary history that is close to all of those, where these might have come from. That's one way how it might be used. Okay, that is just the number of mismatched positions. Now, how can we potentially get an FPT algorithm for this problem? Again, the parameter here is the distance. So this is more reasonable in the sense that it might be interesting in an application to find a consensus string that's not very far away from all those strings. So k might actually be small. A useful tool here is the idea of a dirty column. The idea there is you line up the strings in a matrix, one below the other. And so this is string S1, S2, and so on. And then you have the positions as columns in the matrix. So that might be position 0, position 1, 2, 3, and so on. And a dirty column is just any column where not all characters are the same. So I guess a clean column would be the same letter in all of the strings. That's clean. And anything else is dirty. So wherever you have some mismatch, and it doesn't matter how many then, wherever you have a mismatch, that's a dirty column. And if you think about it, for a consensus string, this is going to be the columns where I have to make a choice. I can either pick in this column, if I want to make all strings happy, I'm out of luck. I can only pick either an A or a B or a C to make some of the strings match with this position, but I can't do it for all of them. So the first observation is if we have many of these dirty columns, it's not going to be possible to find a consensus string. Formally, what does many mean? If we have m strings of length L as before, then m times k is the maximum number of dirty columns where we still have some hope. Right? If we have strictly more than these m times k columns, let me maybe steal the picture from the previous slide. Now, if we have more than, lost the, okay, something's weird. If I have more than m times k such dirty columns, no matter what the consensus string looks like, the consensus string will have to pick a letter in each column. And if there are so many dirty columns, even if I try to distribute them according to the m strings, by pigeonhole principle, one string will get at least k plus 1. Right? if I divide this by m, everyone gets a share fractionally of strictly more than k. So I will have one string, no matter what characters I pick, one string will have more than k mismatches, k plus 1 or more. So S without an index was this consensus string or a candidate for that. And the goal was that the distance to all the strings is at most k, so that's a no instance here. So that's my first reduction rule in the sense of kernelization. If I have an input and I can count the number of dirty columns, if that number is more than m times k, I can immediately say no, not gonna work. So far so easy. And that's mostly all we use, with one tiny additional trick. We're doing a depth first bounded search again. There will be a parameter d, which is the number of differences I'm still allowed. It's my budget of differences I'm still allowed to make. If that's less than 0, then I'm out of luck. If I find some string according to my current string and the string, and I find a string where I'm more than k plus d away, so I'm not allowed to make more than d modifications, and that even if I do all of those, I'm still larger than distance k, then it won't be possible. So why this case is correct needs a justification. The easy case is if I found my current candidate string s has distance less than k for all of the strings, then I'm already happy. Then this is my consensus, and I can return it. The usual case will be that there's at least some string where I have distance k to, but hopefully is not too far away. And I guess I should have listed the initial call. The initial call should be with some arbitrary string, say s1, and I'm starting with k, so I'm allowed to make k modifications. So we'll come back to justifying this first part on the next slide. But let me explain the recursive calls first. There's one more little trick there to reduce the fan out. The usual case is there is some string, and with the current candidate, there's more than the allowed number of mismatches. So that means I have to modify my candidate string by essentially copying some positions from this string si. Otherwise, I don't get rid of these mismatches. So the question is, how many should I copy and which ones? I don't really know. So first, P is the set of all positions where there's a difference, right? Where's the mismatch between current candidate and this specific string si. And now the trick is to choose just a subset of these positions. These are all mismatch positions, but I'm only choosing k plus 1 of them. In this case, that the distance at least is strictly larger than k, so there's at least k plus 1. But there might be more than that. There might be up to 2k initially. The point is that I don't have to choose all of them if it's not possible for any such set p prime with one of those positions to satisfy recursively the consensus string properties, then I'm out of luck. I don't have to try all positions. It has to be possible with one of those, otherwise I'm never gonna get close enough to this string. I don't have to try all positions p, only those p prime. Because even if trying any of the other positions and leaving all the positions in p prime unfixed would still be too big a distance. And then for all those, we recursively try fixing that position. So we take that position in p prime, we update the column P to match that string SI. And then we try to recursively fix from there. So we take that new candidate and one less modification allowed. If the return value of this ever is a valid consensus string, it must have come from this base case, and then we're happy and we return it. And if neither of these k+1 options works, then we're doomed. There's no way to find a consensus. And so let me just briefly say how big the search space is. We're branching out with k+1 here. Because that's the number of different recursive calls. And the depth is, I'm stopping when d is negative, so I branch out with depth at most k. And you can show that this is essentially the same as k to the k, which is what appeared on the slide. Yeah, maybe we'll stop here. I mean, this the rest is a simple argument, but maybe it's not useful to rush it. So we'll briefly visit this tomorrow again and finish off the justification why that algorithm works. Now here you see the search space is still really big. K to the k is not great. On the other hand, if k is very small, it might be practical indeed. Good. See you tomorrow.